Hi class, today we're going to go over the last element of the differentiation topic, first differentiation topic in Year 11, and we're going to look at rates of change today. What that means, how to calculate the average rate of change of a function between 2 points, how to work out the instantaneous rate of change at any point, and that'll be using differentiation. We're also going to then apply that directly to some displacement, velocity, acceleration type questions where we will be given a formula for displacement, and we can use differentiation to work out the velocity and the acceleration of this a particle or a point at any time in the future. So a couple of the key things, as I said, in this section we're going to use differentiation, obviously that's the current topic, to calculate the rate at which a system changes with time. This is probably the first time now that we're applying our differentiation, and in this course this is the principal part where you will apply it. Now rate means how quickly things are either speeding up or slowing down, or increasing or decreasing. So with differentiation we can do that for any system as long as we have a model or an equation for that, how that system is changing. We could use graphical methods if we have a graph of it but don't have the function, but primarily you're going to have functions where you'll be given an equation, and you can use differentiation to determine how that system's changing. So some examples of some systems in this course. The systems are mainly populations, population of humans, population of animals in certain habitats. It's an example question we'll look at shortly. You could also have share prices, commodity prices, or any prices that you could model with an equation. You could work out how that price is changing with time. Temperature is an interesting one, which we'll look at in the next topic when we look at exponentials and logs, but how temperature changes with time. For instance, you might make coffee in the morning, and how does that temperature decrease if you don't drink it straight away and you leave it to cool down to room temperature. We're then going to, as I stated on the last slide, look at the motions of particles and look at terms called displacement, velocity, acceleration, what they mean, and how we can calculate them. So let's have a look at a couple of the fundamentals. The first one being we're going to look at how to calculate these two quantities. So if we have some quantity, that could be population, it could be temperature, it could be a share price. We're going to call that Q, just a pronumeral. The average rate of change, we're going to work out how to do that with respect to time for the quantity, and we're also going to look at how to work out the instantaneous rate of change. So firstly, the average rate of change. So if I have some function, you can see here on this blue line, some function between points 1 and point 2, what is the average rate of change? Well, we can see if we connect a line between 1 and 2, the gradient between them, it has a positive gradient, and obviously the blue line is increasing in value. So we know it's the average rate of change is positive, getting larger, but what is it specifically as a number? And to do that, you might recognize this type of equation. If we look down here, all we're really doing is working out the gradient. If I have a function, when we can work out the gradient either between 2 points or at a point, that is telling us the rate of change. It's really at the fundamental heart of this whole first topic and differentiation. So to do that, if I know the value of the quantity at 2 and at 1, I can subtract those from the difference between these two quantities, and primarily we'll be doing questions where things are changing with respect to time. So it'll be t2, whatever the time is here, take away t1. Essentially it's just rise over run. Instantaneous rate of change, well, that's when we're going to use differentiation, because the instantaneous rate of change tells us how things are changing at a point. So if we can get the first derivative and substitute the value at that point into that first derivative, or that gradient function, we might want to call it now a rate of change function. It'll tell us exactly how the system is changing at that point. So you can see in this diagram here, if I knew the equation to this line here at point B, getting the first derivative and subbing it in would give us the gradient of this red line here. And you can see at B, it's changing sort of quite rapidly, and that change is slowing down. By the time we get to point C, you can see the gradient of this line, or tangent line at C, is not as large as it was at B. So the speed is slowing down, or that rate at C will be a smaller value than will be at B. And if we wanted to know if we differentiated this function to work out the rate of change at C, we would sub in 2.5, and at B we'd sub in 1.5. So let's look at an example question. We've got the number of birds in a habitat increases according to a model we've been given. The number of birds n is equal to 2t squared minus 3t plus 60. And importantly, t is the time, and it's in months. Calculate the initial number of birds, the average rate of change in the number of birds between 5 and 6 months, the number of birds after 3 months, and the rate at which the number of birds increases after 3 months. So firstly, the number of birds initially. Well, the word initial in any of these questions is t equals 0. It's the start of the problem. And so if we substitute t equals 0 into the equation, obviously we're going to get 2 times 0 squared minus 3 times 0. Both of those terms will be equal to 0 plus 60. So at t equals 0, or initially, the number of birds is 60. Now keep in mind, any equation that you ever use, the constant value will be the initial value of the population. If we were to graph this function, this would be the y-intercept, as you already know. So that's part 1. Part 2, the average rate of change between 5 and 6 months. Well, if I was going to work that out, the average rate of change would be the number of birds at 6 months, take away the number of birds at 5 months, all over the time at 6 months, which is just 6, take away the time at 5 months, which is 5, which is identical to this term we had here. I'm just rewriting that. So we'd have to work out the number of birds at 2, the number at 1. Obviously the denominator here is just going to be 6 take away 5, which is going to be 1. So how do we work out the number of birds at 6 months? Well, we're just substituting 6 into that equation. So 2 lots of 6 squared minus 3 lots of 6 plus 60. After 6 months, there were 114 birds. I might just put a subscript 6 here and a subscript 5. After 5 months, if we substitute 5 in there, we're going to get 95 birds. And so the average rate of change between 5 and 6 months, 114 minus 95, all over 6 minus 5, which we know is going to be 1. And that gives us a value of 19. The average rate of change between those 2 months was 19. Now we need to put some units here. It's going to be 19 birds per month. On to part 3, the number of birds after 3 months. Well, that's going to be pretty straightforward. Just like we did in the last part, we're going to substitute 3 in for our time, so 3 squared minus 3 lots of 3 plus 60, and that should give us 69 birds after 3 months. Now part 4, the rate at which the number of birds increases after 3 months. Well, this hasn't sort of said it specifically here, but this is asking for the instantaneous rate of change. So to get that at a particular point, we're going to get the first derivative of our function. So dn dt, if we differentiate 2t squared minus 3t plus 60, we should get 4t minus 3. And now the value after 3 months, well, if we substitute t equals 3, 4 lots of 3 is 12, minus 3 would be 9. So the rate at which the birds are increasing after 3 months is 9 birds per month. Always got to have this rate in each of these real life questions. The next part we're going to go through is the motion. I would really encourage you to write this down in your books. Displacement, generally given the pronumeral x, and it measures the distance of any object or particle from the fixed point, or what we call the origin. Displacement is a little bit different than the term distance. Not the distance traveled, but displacement. How far is it from the origin? Velocity, or another name for velocity, which I've written down there anyway, is speed. How fast is a particle traveling? Or if you like, what is the rate of change of the displacement? And to work out the velocity, if you have a displacement equation, which you'll be given a lot of in this 6.10 exercise, to get the velocity, we just get the first derivative of the displacement. Acceleration is a measure of how the rate of change of the velocity. And to get the acceleration equation, we would do the first derivative of velocity. So the way that they're connected in this particular differentiation topic, if I have displacement, differentiate to get velocity. If I have velocity, differentiate to get acceleration. If I have displacement and I need to get to acceleration, I have to do two differentiation processes. Next year in the Year 12 course, we're going to do integration, which is the opposite operation, and which means if I have acceleration or velocity, I can integrate to get to what I need. So let's look at a couple of examples to finish off. An object's traveling a distance according to a function capital D equals t squared plus t plus 5, where d is in meters and t is in seconds. Find the speed at which it's traveling after 4 seconds and 10 seconds. So this is basically telling us our displacement, or it's an equation for displacement. So our velocity is going to be the first derivative of this displacement formula with respect to time. So if I differentiate that function, we'll get 2t plus 1. All we're left to do now to find the velocity at those two times is substitute 4 and 10 into that equation. So for part 1, it will be 9 meters per second. Now we can write meters per second like this, but I would encourage you to start writing anything to do with speed like this. Meters, write the seconds next to it with a little -1. And 2, well, the velocity after 10 seconds, that'll be 2 lots of 10 plus 1, and obviously that will be 21 meters per second. On to the last example. A ball rolls down a ramp, and its displacement is given by this equation here. X equals 16 minus t squared. Part A, find its initial displacement. We remember from a couple of examples ago, initial always means t equals 0. If we substitute that into the equation, initially this ball is 16 meters from the origin, wherever that may be. Part B, find its displacement after 3 seconds. Well, that's just substituting 3 into that equation. 16 take away 9, it's going to be 7. Now, we just need to go back here. The units here are centimeters, so we're 7 centimeters from the origin now. Part C, find its velocity. Well, velocity is equal to the first derivative of the displacement. So we firstly find that equation. You can see here that the constant term 16, that will disappear when we differentiate, and we'll be left with minus 2t to the power of 1, or minus 2t. After 2 seconds, our velocity is equal to minus 2 lots of 2, which is minus 4 meters per second. Part D, show that the ball has a constant acceleration of minus 2 centimeters per second minus 2. So the units for velocity will always be the time unit, in this case seconds to the minus 1. Acceleration will always have second to the minus 2. That's something you'll get used to with practice. So our acceleration, if you go back a couple of slides, is the first derivative of velocity. And if we differentiate this equation here, this expression minus 2t, we'll get the expression minus 2. So just doing that alone, we've actually completed part 1. We've completed this show simply by differentiating. So we can say here that the acceleration of this particle is always going to be minus 2 centimeters per second. So it's always accelerating back towards the origin. So it could be something like, it could be a ball on a ramp, but on a spring, for instance. Okay, to practice those skills, I'd like you to go to page 457. Actually, we'll make it, that's actually an error there. We'll make that page 315. Exercise 1 to 10. Question 1 is just asking you what's the rate of change. So it's just wanting you to differentiate. Be mindful, I'm sure in the textbook, if there's a little dot there, that means pi. But your main focus should be on these questions that have multiple parts to them. Good luck, and I'll do another video going through some of those questions as well.